Semicircular wires. An electric current I flows through a semicircular section of a wire of radius A. What is the direction of the magnetic field at point P? And what is the magnitude of the magnetic field at point P? A second semicircular section of wire with an equal and opposite current is placed next to the first one. So in this case, the current's going this way, the top loop it's going this way. What is the net magnetic field at point P? And what kind of changes must be done in order to cancel the magnetic field at point P? And explain. What is the direction of the magnetic field at point P? The horizontal sections of the wire, which is over here and here, do not contribute anything to the field at point P. The cross product, here we're going to erase this for a second, the cross product, and we're going to use the Biot-Savart law, of a line segment ds, so here would be ds, and the unit vector r, which is pointing to P, which is where we want to find the magnetic field, those are parallel. So the cross product is 0, so there's no magnetic field. And in this case here, ds is this way, r hat is this way, the cross product is still 0. So now just go to the semicircle, grab the wire with your right hand, orienting your thumb in the direction of the conventional current. Your fingers curl in the direction of the field, indicating a magnetic field into the page at point P. So the magnetic field is like that at point P. The magnetic field at point P is due only to the semicircle. We also know that ds, wherever we take it on the semicircle, will be perpendicular to the unit vector r that points to P. So therefore, this expression here in Biot-Savart, you have ds cross r, the magnitude of that is just ds, and the cross product is just ds r sine theta. Theta is 90 degrees, so ds cross r, the magnitude just reduces to ds. And of course the I comes out in front, that's a constant. We now sum up all the little ds's. However, this time, and let me erase this, we don't have a full circle, unlike what we did in the presentation. We only have half a circle. So when we add all the ds's up, we only get pi r, or in this case, since the radius is a, pi a. We don't get 2 pi a. So then we carry out the little math, and the magnetic field is mu 0 I over 4a. What is the net magnetic field at point P, where we put a second wire in, where it's going like this, the current? Well, the right-hand grip rule showed that the top wire gives us a magnetic field into the page. And if you do the same thing with this wire, you also find the magnetic field going into the page. So the net will be the magnetic field due to the top plus the magnetic field due to the bottom. They both have the same magnitude, right? It's the same geometry. You add the two of them together and you get a net magnetic field of mu 0 I over 2a. What kind of changes must be done in order to cancel the magnetic field at point P? Explain. You can reverse the current direction in either one of the wires. Then one of the magnetic fields will be into the page and the other will be out of the page, and they have the same magnitude, so they'll cancel. Or turn the current off for both wires.